Hello, welcome back to MEC 416/816 Engineering Acoustics. In this video, we are going to start our Chapter 3, which focuses on the acoustic wave equation and some simple solutions. This is Chapter 5 in the book. We're going to start with a discussion of fundamental facts of sound, and then we'll take a look at how sound behaves in space and sound. And then from there, we will go through three important equations and use them to derive the linear acoustic wave equation. So first, regarding some fundamental facts for sound. First of all, sound will travel undistorted. Meaning that as sound waves propagate, they do not distort in any way. Second, sound is going to travel with some delay. Travels with some time delay, meaning that they travel with some speed, typically what we call speed of sound, of course. They don't have an infinite velocity, and so there's going to be some delay in that travel. And then the third aspect is that sound from different sources, will travel independently. Meaning that two sources of sound will not interfere with each other, at least in terms of the propagation of those sound waves. That doesn't mean that two sound sources can't interfere at a particular point of space, for example, at a particular location, but that interference is not going to affect how those sound waves travel through the surrounding medium. Okay, let's go ahead and take a look at how sound behaves in both time and space. So we're going to need to come up with a way to describe sound. And so first observation we can make is that sound can be measured at some position in space. And so by doing that, we will measure the signal. And we'll say that the measured signal is a function p, which is a function of time in this case. So we're measuring at a fixed location and getting back some pressure signals. So sound waves are pressure fluctuations, as we'll see. So when we measure that sound wave at a particular position, we're going to get a function of time. Additionally, sound can also be measured at two locations at one time. And so that also then tells us that sound must depend on space. So our pressure measurement can depend on locations in space. We'll use x, and that underline means a vector quantity. And in this case, x is actually a vector in R3. Vector in R3. So this R here, this script R, is the set of all real numbers. And when we put a 3 in the superscript, that means that we're looking at a three-dimensional vector. So we're talking about a pressure measurement taken in three-dimensional space. Okay, so clearly then, sound must be dependent on both space and time. And so what we can say here is that the pressure P of x, t is, well, it's simply a function of space and time, and we're going to find this to be the sound pressure. Okay, so if we now consider 2 points, x1 and x2, and then we look at the sound at those points, we'll say P of t, and then we'll use Q of t. We can then start to discuss how these two signals relate to each other. So first of all, we're going to know that clearly the sound at two different points in space are going to be different, but they're going to be related in some sense. And what that really means is that the sounds are going to be the same except for some kind of time delay. So, and that we can say then that P of t must be equal to Q of t plus a delta t, so there's that time delay. And then from there, we've said that speed travels at the speed of sound, which we'll say is c. Then we can relate that that time delay to the distance between point P and point Q, and say that delta t here is equal to r divided by c, where r is the distance, from P to Q. Then finally, we can write that P of t is equal to Q of t plus or minus r divided by c. And this is then very comparable to what we saw for traveling waves when we studied those for the elastic wave equation. Okay, so let's move on and talk about the acoustic wave equation. For the acoustic wave equation, we're going to need three important equations. The first is the equation of state. The second is the equation of continuity. And then the third is Euler's equation. Before we go through this analysis, we're going to make the following assumptions. First, we're going to assume that the fluid is lossless. Second, we're going to assume that the fluid is inviscid. It means that all of the viscous forces are negligible. And one thing I'd just like to mention that when we studied elastic waves, we were studying vibrations in solid bodies, solid objects. We're studying oscillations of solid bodies. When we talk about acoustics, we're then studying oscillation of fluid bodies. And that can both be a liquid such as water, or it can also just be air or some other gas medium. The third assumption we're going to make is that of small displacements without a pressure change. Small displacements without pressure change. And last assumption we're going to make is that the continuum assumption holds. Meaning that when we look at a fluid body, there is material everywhere. We're ignoring the fact that there are atoms, molecules, etc. We are assuming that there is material everywhere. So under these assumptions, we can define what is called the acoustic pressure. And the acoustic pressure is some fluctuation about the atmospheric pressure. So the atmospheric pressure is the mean pressure. And then sound waves are then small fluctuations about that pressure. So we can write that the acoustic pressure P of x comma t is equal to the total pressure, and this underbar here represents a capital P now, so there's not a vector, it's a scalar. So we have a capital P function of x comma t minus P0, which is our atmospheric pressure. And so on the right here, we have the acoustic pressure. On the left, we have the acoustic pressure. On the right, first term, we have the total pressure. And the second term on the right is the atmospheric pressure. Okay, so we're just going to briefly draw what this looks like. So first, let's draw our acoustic pressure. So this is our P0. So the acoustic pressure in blue here is just a constant line. And then the total pressure is going to include both the small fluctuations due to sound waves and the atmospheric pressure. So this is, in green here is our total pressure. In blue we have the atmospheric pressure. And I'm just going to duplicate that green line. And I'm going to change the color. Let's make it red. And this red line now is the acoustic pressure. So you can see here that an acoustic or a sound wave is a small oscillation in pressure. Okay, another thing we're going to need to use is the fluid particle displacement. This is written as a vector, so it's a vector quantity, which is a function of a vector position and time itself. We'll then also look at the fluid particle velocity, and we'll write that as u, which is a vector function of a vector and time. This is equal to the partial derivative of the fluid particle displacement with respect to time, or we could write that with the subscript notation that we've been using, so because c sub t. And again, because c is a vector. So acoustic pressure and pressure in general is a scalar quantity, but it's a function of the vector x. If we come back up here, x here should be a vector, meaning that it's a three-dimensional point in space, but the pressure itself at that point is just a scalar variable. Whereas the fluid particle displacement is a vector function of a vector in time. So that means that at a particular point in space, so that will give us that vector position, the fluid particle displacement itself is different in each direction. So that you will have a particular displacement in the x direction, y direction, and z direction at a particular location in space. We're not going to go too deep into this vector stuff, and we're not really going to do any kind of continuum mechanics or vector-based calculus here, but these are things that do show up when you study continuum mechanics in general. Okay, so we're going to stop here, and in the next video, we're going to go through the equation of state.